This is Phil Koopman with a tutorial on lifecycle and configuration management. A product lifecycle has to do with the entirety of the creation, use, and retirement of the product rather than just the product development part of that. You can think of a lifecycle as a circular cycle of identifying a need, creating a concept, designing a product and its manufacturing process, production, deployment, support and maintenance, upgrades, retirement and disposal, and then back to the next opportunity. Some specific issues related to the lifecycle we'll talk about in this tutorial include version control, which is keeping different versions of the software and product straight, configuration management, which is knowing what's in a deployed system, lifecycle support after development, and dealing with the fact that old embedded systems don't really ever die. That means you have to deal with spare parts for obsolete systems, midlife upgrades, and so on. The anti-patterns for lifecycle issues include not having version control, not having configuration management, and implementing features incrementally but never stepping back to have a baseline configuration. Configuration management is not something that figures prominently in a typical software course. However, it can cause real problems and even deaths in the real world. In 2015, an Airbus A400M flight crashed because of a configuration management error. 3 out of 4 engines in the aircraft had corrupted torque calibration parameters. By design, for some reason, the pilots only get warnings when they're 120 meters off the ground. Then the engines throttle back or shut down. So that means the aircraft took off with bad configuration, got up in the air, and then lost 3 out of 4 engines. The pilots attempted to land but were unable to do so successfully, resulting in a crash that killed 4 out of 6 crew members. Afterwards, someone associated with this said they never imagined they'd lose 3 out of 4 engines. But a bad configuration can be a common cause failure that causes multiple redundant systems to all fail together. 2 related concepts are version control and configuration management. Let's start with version control. A version control system stores and navigates snapshots of different versions of the software. The idea is if you have a piece of software and you make a change, after you make the change, that's a different version than the one before the change. This is typically done at a much finer grain than releases of software, all the way down to individual changes. A version control system gives you the ability to roll back to a previous version. So if you've ever made a mistake with a change and want to get back to where you were when the software was still working, the version control system would let you roll back to the working version. It also synchronizes compatible versions. Maybe there's a development versus a release version. Maybe there are different branches and merges of parallel efforts for different ports to different hardware and so on. The idea of a version control system is to keep all this straight. So if you have a specific version number, the version control system can give you the actual source code that matches that version number. There are many popular version control systems and they change all the time. It doesn't really matter which one you use as long as it is good for your purposes. Git is a currently popular one, but really use one that does what you need. To consider when picking a version control system is that if you need to manage binary files instead of text files, some systems have trouble with that. Also, if you have multiple sites concurrently accessing the version control system, that can require special care. For a long-lived embedded system, you want to do more than the obvious putting the source code for the software itself in version control. You also want the design documents, the requirements, the test plans, the tool chain, and other related artifacts in the version control system so that if you have to go back and, for example, fix a bug in an old version without being able to upgrade to the new version, you can actually figure out what the tests were to make sure that that bug got fixed properly, for example. You also need a process for who, what, and when to update a version. Minor versions might be created every time there's a small change to the software. but at some point you decide that a particular version is a stable version, something you want to track at a higher level and make sure you can get later, and you need a process to sort all that out. You also want to tie your version control system to some sort of disaster recovery system. What if, for example, there's a fire at your development building and the computers are destroyed? How do you recover all that software you spent all that money developing? Your disaster recovery system will take snapshots of the version control system and store them off-site so that you can withstand fire, flood, crypto locker attacks, and so on. Configuration management is an approach that works with version control to figure out what's in a particular system. This is a picture of a bolt that's put into an Airbus 380 aircraft, and you can notice that there's a stamped-in lot number in the bolt, so that if something goes wrong with a bolt in the field that identify as, oh, this bolt has a problem, they can figure out what other bolts were from the same source and the same batch. That way, if there's a systematic error with the manufacturing or inspection of a batch of bolts, they can track down all the other bolts and replace them so that they don't have a bad outcome. Software is a little different in that it's not manufactured in quite the same way. But in a similar way, you want to know what version of software is in a system so that, for example, if there's a problem with that system, you can figure out what other systems have that software with that same bug. Configuration management is all about being able to identify which version of hardware and software is installed in a particular system or a particular set of systems. You might want to know this because you want to know if it is a version that has a particular bug fix that turns out to be a problem, whether it's a version that has a specific feature so that you know which test to run, because if the feature is not there, it's going to fail the related tests. And if you're upgrading a system, there might be a dependency that a certain version has to already be installed before you can update to the next release. You also want to know which version of software is in a failed product, so you can go back to the version control system and pull out the corresponding software to look for where the bug is. Beyond the obvious of configuration management telling you what's installed in a particular system, you want to go a little bit deeper for a long-lived embedded system. You should snapshot every software build that's a release candidate and record its manifest. The manifest is the list of all the components in it. For example, if you have a build process that builds a bunch of different source codes and a bunch of different libraries, you want to know the version numbers of all the source code components and the version numbers of all the libraries, so that if you have to go back to the version control system, you can ask for all the right different versions and replicate the software for that build bit by bit. You want to make sure that return units can self-report their version. While it's nice to think that you can keep records of which version goes in which system, that never really works in practice. In part, it's just too easy to have a gap or a mistake in making the records, but also by the time field technicians do updates and so on, the only real way to know what's installed in a system is to ask it and have it tell you which version number is in its configuration. That includes the software source code, the libraries, the drivers, and so on. You also need, in addition to the software version, the hardware version of the different components, and the configuration data version if applicable. Configuration data might be specific data fields that get programmed in along with the software to, for example, inform you whether the system should be operated in English versus metric units, or which features are supposed to be activated in this particular version of the system. As I mentioned, you can try and track this in a central database, but that never really works. You really want units to self-report their own configuration. You also need to know which software is compatible with which hardware. You will essentially never get a case where a large fleet has all exactly the same hardware. There'll be different versions, there'll be different subversions, there'll be components which have different versions of firmware installed, and so on. If you want to reproduce a problem or know that an update will be successful, you need to be able to recreate a build, including the software and the hardware. And by the way, don't forget, the tools to do that might be obsolete, so you might have to recreate the tool chain as well. Finally, in a particular system, there can be feature activation, which is the features that have been licensed by a particular user. It's common in embedded systems to have more functions built in than you initially sell, and then have users pay additional fees to activate those other features. If you're trying to track down a bug, or you're trying to recreate a system after, for example, a spare part has been installed and you need to reprogram it, you also need to know which features are supposed to be activated to restore the system to its proper operation. As an example of the type of configuration management information you'll see, here's a paper tape printout I saw at a gas pump that apparently had just been rebooted when I was buying gas. You can see that when it powers on, it prints out configuration data. It has the revision number, the software revision number, as a checksum to make sure the software actually matches the revision that's supposed to be there. In this case, the serial number wasn't programmed in for some reason, but it also has operational configuration data, whether it preheats, the paper temperature, the auto advance, serial port information, and so on. An interesting thing to note is that it says the watchdog timer is on. While I was not involved in the design of this system, I imagine that's because someone accidentally forgot to turn it on after testing for deployment, and this is a way to make sure that it's actually been turned on before you ship the system out. And finally, the letters and numbers at the bottom look like a test of the character generator to make sure the printer is up and operational so that it can be put into use. Once you've gotten configuration management and version control handled, you have to also deal with the fact that embedded systems live almost forever, at least some of them. 10 to 50-year life cycles are surprisingly common for embedded systems. As an example, the Sage air defense system, which was built with vacuum tubes, started in 1954, deployed in 1963, had 500,000 lines of code, and operated for another 20 years. The 1A ESS telephone switch, which was a computerized telephone switch, operated from 1976 through at least 2008. And there might still be one kicking around in some small phone company someplace for all we know. Aircraft can easily operate for 25 to 30 years, sometimes up to 50 years. Eventually, they get new computer systems, but old computers can last a really long time before being replaced in those systems. Even everyday cars routinely operate for 15 years or more without anyone changing out the engine controller and the other electronics. These long lifetimes bring significant challenges. In addition to maintaining software that's 15 or 20 or 30 years old, you have to consider disaster recovery. What if the company that made your computer system or that made the software components you depend on went out of business? It's common for embedded system companies to insist on a software escrow so that they can recover the source code of their supplier if the supplier goes out of business. What about end of life for hardware and software? What if support for your operating system is ended and you no longer get security patches? What's your plan for that? What if you want to add new services to an existing platform and it runs out of steam? Do you have to buy all new hardware for all your customers so you can add the new services? And what do you do about security if you have trouble updating all the systems in the field? If you have a short-lived system like consumer electronics, it's easy enough to say, we'll make all of them the same, we'll keep all the software up to date, and when that gets too hard, we'll just brick them and tell the consumers to buy new ones. That approach might work okay for semi-disposable consumer electronics, but it doesn't work so well for airplanes and cars and high-value systems that are supposed to last a long time. You have to deal with realities such as the original hardware at some point can't be upgraded because the memory's full and the CPU is 100%. So you have to decide what to do about that when that happens. While consumers are used to updating their hardware and software for their consumer electronics devices every year or 2 or 3, long-lived embedded systems, especially specialty systems, can't just do that. There's a tremendous amount of engineering effort required to build these systems, and the point of having them is that they last a long time. You don't exactly throw away a nuclear-powered submarine every 3 years to go to the next model. You just don't have enough billions of dollars to do that. This results in situations such as Britain's strategic missile submarines running on Windows XP in 2016, and probably still are. An additional example is that it's quite common to see medical equipment running on Windows 95. This creates a dilemma for hospitals because Windows 95 is quite vulnerable to security attacks. And, even worse, hospitals typically are not allowed to patch their systems because if you make a change to a system, you have to revalidate safety, and that includes security patches. This results in a real life cycle dilemma. You have an obsolete operating system, and you're not allowed to do security patches, but you're being attacked and your equipment is being compromised. There's no easy answer to deal with this in a life-critical system. On the other hand, you really wouldn't want to be subject to a piece of medical equipment where software changes have been made willy-nilly and no safety review has been done on those changes to make sure the system's still safe. This results in a difficult situation. It's not easy to resolve this problem. Best practices for lifecycle management have to encompass configuration management, versioning, and dealing with long-lived systems. Make sure to take configuration management and versioning seriously. They're different. Recall that configuration management is about knowing which version's in a particular product, while versioning is keeping straight, okay, I have a version number, but where's the source code, how do I rebuild it, and so on. Making all this work requires using a formal build process to create and release your product. Ideally, this entire process is automated based on configuration management data. You can query a particular product to find out exactly which version's in it, and you have an archive build script that knows for that version of product, here are the versions for all the different pieces, here are the versions of tools used to build those pieces, and so on, so that at a push of a button, given a version number, you can absolutely recreate the complete binary image form source code for that product. That gives you a basis to do diagnosis, to make changes, and so on if there's a downstream problem or there's a question about what's going on with your particular version of software. Make sure to plan for at least twice the life cycle you think will happen. Embedded systems can live, it seems, forever. And at that, 2x won't cover everything, but it's a good rule of thumb. Make sure you have a plan for product end of life. The components being sold to you will undergo end of life, or you may have to retire your product. Think about that up front rather than when it's a crisis at the end. There are a number of pitfalls for life cycles. One pitfall is releasing the wrong version. It's surprisingly common to build and release a development version instead of a production version, or a debug version with a watchdog timer turned off, and so on. You need a good, rigorous build process to make sure the software you're shipping actually has all the versions of the pieces you think it should have. Another pitfall is cutting corners on software configuration management. If your configuration management's a mess and you have a field failure, it may be difficult or impossible to reconstruct the software inside that product so that you know what was actually going on. Another pitfall is getting caught without replacement parts. At some point, the CPU you're using, or the memory you're using, or other hardware components you're using, or even the operating system you're using will be end-of-lifed. The manufacturer will say, sorry, not going to sell you anymore, or you're not allowed to use this anymore because it's not supported for security patches. For hardware, there will commonly be an end-of-life buy notice, where the hardware vendor says, this is your last chance, buy your chips now, make sure you have enough for all the repair parts you're going to need until you retire your product. Make sure you actually buy enough chips to take you through end of life for the product, or you'll have some big problems downstream. Also, plan ahead for your hardware, storage media, tools, libraries, and so on going obsolete over the life of your product. It's uncommon to have resources to plan for everything and buy an infinite supply of spare parts just in case, but a little bit of thought can go a long way towards avoiding a disaster downstream when some of these inevitable issues occur during your product lifecycle.